All right. Let's just read the introduction together, the first sentence. It says, now that we have a powerful ally on our side, the fundamental theorem of calculus, we begin to explore this strange new world of integrals. It is strange and it's marvelous and it's powerful too. Okay, the couple of topics here to get us going in the world of integrals. One is the idea of indefinite integral, and the other is the net change theorem that I might have mentioned last time. Okay, so that's just getting us started. And let's start with the indefinite integral. The indefinite integral can be seen as an entire family of functions, functions whose derivative is the integrand, okay? And then I say take a good long look on page 403. Now you'll find on page 403 a lot of friendly faces there from section 4.9, where we were talking about it's basically the antiderivatives of functions. But we're giving it a new name and subtly a new idea too, which is to say the indefinite integral is tied to the integral. Like, for instance, you could say the integral of, say, 3x squared minus 2x plus 1 dx. Well, when we were putting limits on the thing, what we did was we looked for the antiderivative. And if we look for the antiderivative, we get 3 times x to the 3 over 3 minus 2 times x to the 2 over 2 plus x plus c, which reduces down to x cubed minus x squared plus x plus c. Okay? Then we would apply the limits and we wouldn't put the plus c, but this time what we'll do is we're not even interested in the limits. We're just going to call this a new thing. Back in section 4.9, we called this the antiderivative, going the reverse direction, the antiderivative. But now instead, we're going to say that this, and I'll put this down here again like so and make a sentence out of it. We're going to say that this guy right here is the indefinite integral. All of it together, the indefinite integral. Indefinite in that there are no limits. Okay, so all of this together is a statement. Okay, it says the indefinite integral of 3x squared minus 2x plus 1 is x cubed minus x squared plus x plus c. And you can write that out if you want to. The indefinite integral of what am I using shorthand for? This is important. The indefinite of 3x squared minus 2x plus 1. And I can call him a name if you want. I can say that's like f of x, right? Is equal to, and I'll call him a name, capital F of x is x cubed minus x squared plus x plus c. So that's a language, a math language. The indefinite integral is this guy. But last chapter we called it the antiderivative. See how what's happening is the idea of definite integral, area under a curve, taking limits, and the fundamental theorems of calculus tie this together. And so we're no longer really going to use the name antiderivative, although that's really what it is, but instead we'll call it the indefinite integral. And it actually is another function. And as I say up here, it's an entire family of functions, because remember, c could be 1, c could be negative 5, c could be, 1 over pi, c could be even 0, whatever you want it to be. There's a whole slew of functions that serve. So in this section, you're going to be anti-deriving again, except you're going to be calling it the indefinite integral. Don't forget the plus c on every single answer that does not have limits, okay? This section says, find the indefinite integral. Then it says, okay, evaluate the definite integral. And this book, he has a warning. He goes, listen, the definite integral, the one with limits, is a number that you compute. It's a value. The indefinite integral is a family of functions that you find. But to find the definite integral's value, you go to one of the indefinite integrals, one of the members of the family of antiderivatives. It's crazy. But you'll see, that's the language, and you should be confronted with it. Now, before we go on and finish this section, because I think we'll do this in one video, here's a little guy that says, verify if this formula is correct. And what it says is the antiderivative, it's claiming definite integral of the natural log of x, let's call him f of x, of f of x equals the natural log of x is capital F of x, this family of functions, x natural log of x minus x plus c. That's the claim. How do we see if it's true or not? Well, if you're an antiderivative, we're going to check to see if true by finding out, okay, whether or not, a lot of times English is necessary, f prime of x is equal to little f of x. That's it. If you're claiming that this is the indefinite integral, then his derivative, that guy's derivative, needs to be ln. So we take the derivative of x ln x minus x plus c and find out if it's truly equal to natural log of x. And what do we see in this particular problem? Right there, if we're deriving none other than product rule. Okay, so we're going to say derivative of x is 1 times the natural log of x plus x times the derivative of the natural log of x is 1 over x minus derivative of x is 1 plus derivative of some constant is 0. So we're getting natural log of x plus x, see that? Plus 1, I should say. See it? Minus 1. Oh, is the natural log of x. And yep, that's the little guy, f of x. So check, and you are right, sir. That is a true statement. Okay? That's telling you as a student, I can take an antiderivative, I can take an integral, but before I compute with it, let me make sure if I got that right. Or it might be me as a teacher going, see, this is the antiderivative. Like next semester, I do product rule, and I should say integration by parts, and I go, look, take this guy, rederive it, and hey, it's right. It's equal to the integrand. So anytime you antiderive, that's always good to derive back to see if you did it right. Okay, you understand? Check your skill there. So this page here, I've got like 4 different guys to find the indefinite integral for. It's kind of quick work, and that should encourage you. So, all right, so I'm going to look at this. I'm going to look for this guy, and you can too. Go ahead of me if you want and pause and do these 2, and then we'll move on and pause and do the other 2, see if you do them right. But yeah, if you're going to antiderive, you want to watch me do it. I'm going to, in order to do that, if I'm deriving or integrating, which we're doing now, we're going to call it integrating, I have to look at the power. So I'm going to bump up the power by 1 and divide by that same bumped up power and tack on a plus c. Okay, so I've got x upstairs to the 5/3. So it's really, if I invert and multiply, 3/5 x to the 5/3 power plus c. And that's it. That's the indefinite integral of that guy. Moving on. Okay. Polynomials, please. I eat these for breakfast. What about you? Antideriving, we got 3 times x to the 3 over 3. Some of you can start working in your head a little more than I am. Minus 5 times x to the 2 over 2. When there's a constant, put an x and then put a plus c. Rewrite, we have x cubed minus 5 over 2x squared plus 4x plus c. Folks, we're done with that one too. That's the antiderivative. That's the indefinite integral, I should say. It's a new language, okay? Okay. Now these functions can then be used to compute definite integrals once you have them. It's good. Like having the derivative, you have a function that'll give you the slope of a tangent or instantaneous rate of change anytime you need it. Well, these guys will be able to compute the definite integrals for you for whatever purpose whatsoever. Okay. All right. Couple more. I don't know if you remember this one. One of the things you can do, and I'm going to remind you of this, is if you've got a constant and he's bugging you, you can move him out of the integral symbol Question, can I move an x out of the integral? No, you cannot. But if it's a constant, that comes from Riemann sums. It's as if I factored out a 5 from every term in the Riemann sum. So it's a property of definite integrals that we've covered. You can move a constant out. Anyway, this one is a one-liner. Look on page 103, you'll find it. It is tan inverse of x plus c. Are we done? Yeah, we're done. Are you kidding? No, that's it. So some of you are going to forget the 1 over 1 plus x squared, so try to get a tattoo done pretty quickly, haha, but really just basically, you look on page 403 and try to memorize all of it, okay? And a lot of it you already know. This next one, if I put that on a test, I'd lose everybody, just about. Okay, it's a clever one. You need trig. I can't do anything. There's no quotient rule. There's no product rule with integration. It's just what you see is what you try to get, okay? In this case, I see sine 2 theta, and since I teach trig a lot, or I teach this class, I go, sine 2 theta, I know what that is. You're right. You pause it and look it up. Go ahead and pause it. I said pause it. Okay. If you pause it, what you found is 2 sine x, or theta, cosine theta. Why is that a big deal? Well, the sines cancel. Oh, thank goodness. It's a setup problem. In fact, I'll move the 2 out of the way, and really you're looking at cosine. Why didn't they say so? Well, we're finding that out. We have to do lots of stuff. This is why I say before you get into calc, be sure you're good at algebra. Be sure you're good at trigonometry. Then you're good for the class. What's the integral, or what's the antiderivative or the integral of cosine? Of course, it's sine plus c, and that's it. Fantastic. Fantastic. Okay, so I was going to stop the video there, but I'm going to keep it rolling. I'm going to go down to this. There's one more problem to do, but it takes a little bit of talking. Hang on there. This is the net change theorem. Okay, the net change theorem is not a big deal. What it basically says is whenever you integrate, actually on page 406 he states it, he goes, the integral of a rate of change function, I added function, and I said, for example, velocity equals the net change in the function. So I decided to take a look at problem 62 on page 410 with you guys. They give us an acceleration acceleration function of a particle. They give us an initial velocity, and they give us a time interval. So the first problem is find the velocity, and we did this in section 4.9. So we already know this part. We already know this part, right? Watch. Okay. So since the acceleration function is 2t plus 3, we know to get to the velocity function from last chapter, we have to anti-derive. Okay? That's what we have to do. You can look at it that way, or you can say, hey, the velocity function is equal to the antiderivative of the acceleration function, or the indefinite integral of the, that's why we invent this language, is the velocity function is the indefinite integral of the acceleration function. Okay? So when we do you get that? That language is pretty good. Okay, so when we look for this guy, we've done it before, we actually go ahead and we anti-derive, or we find the indefinite integral of the acceleration function, if that makes sense. I hope it does. Remember, derive velocity to get to acceleration, anti-derive acceleration to get to velocity. Now we're saying it differently. We're saying the velocity function is the indefinite integral of the acceleration function. So let's do it. Pretty easy. We go 2 times t squared over 2 plus 3t plus some sort of c. So the velocity function is t squared plus 3t plus c. Now before you go on, here comes the initial velocity story. The initial velocity they gave us was v of 0 is actually -4. Okay, so that means when we plug in 0 into our function, 0 squared plus 3 times 0 plus c, it should be -4. which means that c is -4. Did you see that coming? So our velocity function, this is what we want. It turns out to be t squared plus 3t minus 4. And step 1 is complete. And now step 2 is coming. This is something new. Find the total distance traveled over the given time interval. What's the given time interval? I'll put it up here. So there he is. 0 less than or equal to t less than or equal to 3. That's the time interval. Think of t as in seconds. Okay. Now the funny thing is, is this thing's in motion. And did you notice that his initial velocity was negative? It's interesting. Without really needing the position function, what's happening is, over this time interval, 0 to 3, is the thing always going in a negative direction, or does he change? What's the velocity doing? Okay. In fact, if we were to graph this velocity function, what would it look like? Okay. One of the things you could do, this is good. Why would I set it equal to 0? Well, I want to know the sign of the velocity. Let's find the sign of v of t. Because it's going to be negative, it could be positive, it could be whatever. So we set it equal to 0. Something I'm teaching right now in Algebra 2 is quadratic inequalities. Okay, and he factors, I think, nicely. It's t, plus 4 and t minus 1. Is that right? Okay, so we get t is -4, and we get t is equal to 1. Look at the time interval. We don't care about t is -4, do we? We don't. We're just looking at this time interval and put out a number line and go from 0 to 3. But guess what? We got this so-called critical number. Put him here as 1. And I bet what we're going to find out is that the velocity changes sign, because right here at 1, when t is equal to 1, let's say the velocity of 1 is 0. That means he's standing still. He's changing his mind. Okay, so if you were to plug in, say, t is equal to 1/2, what happens here? Look right here. What sign do we get? We get a positive times a negative is negative velocity. And you can even think of it as it's descending, if you will. Okay, we're not looking for max mins. We're just saying he's negative, but then as soon as you put, say, t is equal to 2 in there, you get positive times positive is positive. So what that means really in this problem, if you want to think vertically, you can, or horizontally, whatever, you have some sort of position, whatever it is. This is when t is equal to 0. And initially, he's going down until he gets to t is equal to 1. And then that means he's going in a negative direction. But then after he stops, he goes back up and he goes to some point up here where t is equal to 3 somewhere. Okay? So, what does that mean? Well, there's two concepts here on this problem. One is you can use, here we go, the definite integral to find the net change, and you can use it also to find the total change or total distance traveled. And I'm going to do both. Okay, we've started this, so it's going to be a longish guy. Just tell yourself, hey man, net change is after he gets through the indefinite integrals, and you can watch it again and again if you want. So here's the thing. This is going to be the net change, and I'll write or displacement. They ask for that also on some of the other homework problems. So here you go. We're going to integrate from a to b, v of t dt is that, the net change. So for us, it's the integral from 0 to 3 of your velocity function, which is t squared plus 3t minus 4 dt. Okay, and so let's see what happens. We have, therefore, t to the 3 over 3. I'm finding a definite integral, plus 3 over 2t squared. Aha, I skipped a step. Minus 4t, definite integral, 0 to 3. All right, so what we're getting is 27 over 3 minus, or plus, that would be 27 over 2. And then minus 12. And in the next go round, it's nothing but zeros, isn't it? So I do my math right? I think so. let's see. I would write, therefore, for this guy, I'd go, well, I take out the 27, and it's going to be 1/3 plus a half. I think that's 5/6, and then minus 12. So we're getting 27 times 5/6. Let's reduce that guy down a little bit by 3, so that's 9 and 2, right? Okay, and then minus 12. So we have 45 halves minus, let's call it 24 halves, and the total looks like it's 21/2. Now, if we're talking about distance, let's see the problem. He doesn't say anything about any kind of units, but that's its displacement. Now, here's the thing. What it did was it started at some sort of position, it went down, and then it went back up again, and its net displacement is right here. This is its displacement. In other words, its change from its initial location is 21/2, or 10.5 miles, or 10.5 feet, or whatever it might be. For the total distance traveled, you got to go this guy and then this guy to figure it all out. And the way that goes is we know that the velocity is negative from 0 to 1. Okay, so here comes the total distance. What he does is he says, you know, why don't you just basically take the absolute value, like he would say, it's the integral of the absolute value of v of t dt. I've seen that in other books, like from 0 to 3 or a to b or something. But once you know that one of them is negative, you just make it positive. You just make it positive. So what I mean by that is the total distance is we're going to integrate from 0 to 1, and it's going to be t squared plus 3t minus 4 dt. Then we're going to go integral from 1 to 3, same thing, t squared plus 3t minus 4 dt. But here's the thing. I know this guy is positive because v is positive. Oh, see it up here? V is positive from 1 to 3. I know this guy's going to give me a negative integral from 0 to 1. So how do I counter that? You ready? I put a minus in front. I just put a minus in front of the minus to get a double negative and make it positive. So clever. And so what do we get here? We have room down here. Yeah, let's finish it off down here. So what we're getting is we already know what the integral is. We're going to go minus, and then we're going to take this guy, which is, what is the integral again? It's t cubed over 3 plus 3 over 2. Now the rest of this I'm just integrating. You really should be pondering, why did he put that negative there? Does that make sense to me? Well, the velocity is negative, so I'm going to turn a double negative. I'm going to get, when you integrate a velocity, you get distance. This right here without the negative would give me a negative distance. Negative would make sense. Oh, okay. It went negative down this many feet or miles or whatever. But when I add it to the positive distance over here, remember you integrate a velocity, you get distance. We're going to get a net change. It's going to be, this is being subtracted from this guy. But if I make them both positive, hey man, I'm getting total distance traveled. Okay, then you have plus also this same guy from 1 to 3, okay? And so you plug those numbers in. Let's see what happens. So I get a negative, and here I got 1/3, all right, plus 3 halves, and then minus 4. And then remember, when I plug in the lower limit 0, I just got 0. You getting used to that one? So in here I got a negative, and let's see what we have. That's going to be sixths, like that. That's going to be 2 and 9. I think that's 11/6. Is that so? Let's see. 6 would be, that would be 2, and 9 is 11, and then minus 4. But 4, another name for 4, is 24/6, isn't it? So in this case, I'm getting a negative, and the distance here is a negative 13/6. So it went negative 13/6 downward, let's say. But by putting the extra negative in front, it becomes 13 over 6 miles or whatever it might be. Okay, then we go over here. Plus, okay, we take this guy and we plug in 3, and we got 27 over 3 plus, what is that again? 27 over 2. We've seen that number. And then minus 12. But then we have this minus guy here, okay? And he's going to end up being, if I plug in 1, I got the same number again. I've got like 1/3 plus 3/2 minus 4. And you know what? He's negative. It means negative again. Okay, so what we're getting is plus, and what was that, 27? Oh my gosh. What was the answer there? We did that already. 27, yada, 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 yada. It was 21/2, wasn't it? So this is 21 over 2, okay? And then we have minus, but watch out, it's a, what do we get there? Minus 13 over 6, because I'm seeing these numbers again and again. Okay, so finally what we have is plus 21 over 2. I hope I didn't rush you too much on that. I just didn't want to go through those fractions again, right? But we've done them. And this guy here is the same as this guy here is what I'm doing. So I'm just going minus, he becomes plus, man. Plus 13 over 6 again. So let's see, I got 2 of those. That becomes, if I do my math right, that's 13 over 3 total, isn't it? Because it's 26 over 6, 13 over 3, plus 21 over 2, common denominator of 6. I've got 39 over here. No. Wrong, Weber. Come on, do your math. It's the very end, right? 26 plus 63, right? The total distance, drum roll please, is 89 over 6 miles. Okay, I mean, this is good right here. Doesn't reduce or anything. I want you to, look, you see how we got the 13 over 6, 13 over 6 again? Look at this picture. Where are you? Right here. The 13 over 6, another color. The 13 over 6 is this travel down here in this direction. But then he's going back up again, another 13 over 6. And then finally, the net displacement was the 21 over 2. Isn't that interesting? So going down is 13 over 6, going back up 13 over 6 again, and then 21 over 2. And if you add it all together, the total distance traveled, I hope you really appreciate that, was this guy. So that's an interesting problem. I remember it being kind of a pain as a student because it's like, oh man, I can't just integrate. What I got to do is find where the velocity is positive, where it's negative, and adjust using the minus sign, okay? That's it for section 4. Good stuff for you guys to do. See you in the next one.